Namaste and welcome back to yet another lecture on the mathematical foundations for machine learning. We were looking at the idea of inner product, and we were looking at the inner product vector space, and we defined what is inner product, what is dot product, and then we concluded the last class saying that look, if the dot product of two vectors is 0, then the vectors are orthogonal to each other. And we asked a question there like, how did we even come to this conclusion? We had no explicit expression for the I mean in the inner product bringing out the orientation or the angle between the two vectors. So the question is, how did we actually get to this saying that look, if the dot product is 0, the vectors are orthogonal to each other? How did we even come to that conclusion? So what we are going to do is, we are going to answer that question in this lecture, and we are going to move further ahead, right. So let us go back to our answering this question. How did the dot product of two vectors being 0 mean that the two vectors are orthogonal to each other or perpendicular to each other? So now what I am going to do is, I am going to take say two vectors u v. So let us take this to be the x1 axis, and let us take that to be the x2 axis. So I am going to have two vectors, this is say u, the vector u, which is making say some angle theta with the x axis, and let us say I have this other vector which is v. Let me take this to be the vector v, which makes an angle, let us say phi, right. Let us say this is going to be the angle phi, which the vector v makes with the vector u, right. So what is the magnitude of this guy? This guy's magnitude is going to be, this is going to be magnitude of u, and this is going to be magnitude of v, right. This is going to be magnitude of v. Now what we will do is we will just draw perpendiculars here, and we will draw this here, right. So what I am going to do is, I am going to take, so this is going to be my u1, and that is going to be my u2, and this is going to be my v1, and that is going to be my v2, right. That is going to be my v2. So that point is basically v1 v2. So this vector is basically v1 v2, and this vector is basically u1 u2, right. This is what we have. Now what are we going to do? So let us get to know what is this point u1. So u1 is basically, if you see by trigonometric ideas, you know that u1 is going to be the adjacent side, this by the hypotenuse, this by the hypotenuse. So therefore u1 is nothing but the magnitude of u into cos theta. Similarly we have u2, which is nothing but, u2 is basically this. So that is going to be my, what is u2? u2 is going to be again opposite by hypotenuse, therefore u2 is going to be magnitude of u into sin theta. Now I can also find out what is v1 and what is v2. v1 is nothing but magnitude of v into cos of theta plus phi. So this entire angle is going to be theta plus phi. So I am going to take it as cos of theta plus phi. So we are going to say that theta is the angle, from here you can see that theta is the angle made by the u vector along the reference axis x1, and phi is the angle between u and v. Therefore v subtends an angle of theta plus phi with respect to the reference axis x1, right. So we are going to have this. And what about v2? v2 is going to be this sin of theta plus phi, right. Now what I am going to do is, I am going to look at the dot product of these two vectors u dot v which is nothing but u1 v1 plus u2 v2. So, this is going to be norm of u cos theta, norm of v cos of theta plus phi plus norm of u sin theta, norm of v sin of theta plus phi, right, theta plus phi. This is what we have, which is nothing but norm of u norm of v into cos theta cos of theta plus phi plus sin theta sin of theta plus phi. Oh, that is interesting. What do we get there? This is other form cos A cos B plus sin A sin B, which is nothing but cos of A minus B. So, what are we going to have? We are going to have the length of u, the length of v and cos phi. Oh, now you get an explicit expression for u dot v which involves the angle between the two vectors. Now, from here if I say if u dot v is equal to 0, this simply implies vector length of u can be a 0, I mean u can be a 0 vector or v can be a 0 vector, or suppose if you take two non-zero vectors u and v, then the only way in which u dot v can be 0 is cos phi being 0, right. Assuming that u and v are non-zero vectors, the only way in which the u dot v, the dot product of u and v can be 0 is by making cos phi 0. What does this mean to say cos phi is 0? This means phi is equal to 90 degrees or orthogonal. Therefore, this implies u and v are orthogonal. Right. So, that is a very interesting thing. So, what do we have? We have u dot v is equal to magnitude of u magnitude of v cos phi, and if it is 0, assume that u and v are non-zero vectors, then if u dot v is 0, then the only way in which you can get u dot v to be 0 is by having cos phi to 0, and cos phi 0 will be 0 if the angle is 90 degrees between them. And we can also see this very clearly, that if you take u dot v could be any number, could be positive, negative, whatever it is. So, what I will do is I will take the magnitude of u dot v. So, that means I will take the absolute value of u dot v. We are going to say that this is nothing but magnitude of u, magnitude of v, magnitude of absolute value of cos phi. This is what we have, which is basically less than or equal to magnitude of u into magnitude of v, right. This is what we have. Therefore, what we say is, we say that absolute value of u dot v is less than or equal to the product of their magnitudes. When will they be equal? This equality will hold good only when phi is 0, that means u and v are in the same direction. So, let us write that. The equality holds if and only if u and v are in the same direction. Right, we will say equivalently, we will see that they are along the same line, that means the angle between them is 0. This implies cos phi is equal to 1, which implies phi is equal to 0, right. And there is a name for this, and this is what we call as our Cauchy-Schwartz inequality, which you would have studied already. This is basically the Cauchy-Schwartz inequality. Right. This is basically the Cauchy-Schwartz inequality. Now what is so interesting about this? We have already defined this idea of orthogonality and stuff. So let us take one more interesting observation here. So suppose I say that okay, let U be an element of a vector space V. Okay, let me make this as okay. Let V be a vector space. We will say an inner product vector space. Inner product vector space, then if U dot V is equal to 0 for all V or for every V in V, which includes even U, for every vector V in this vector space V. What do we mean by this? I have one vector, I am looking for that one vector which is orthogonal to every fellow in that vector space, including itself, right, including itself. When I say for every V in V, and let us say I will put this, U is also an element of V. Oh, this is more important. So I will take U as an element of V. So what do we have? We basically have a vector space here which is V. In that vector space I have these vectors, say V, W, Z, whatever it is, you have so many vectors, and I have this vector U also here. Now what is happening? I want to look at that vector which is orthogonal to every vector including itself, right, that is more important. So when I say every V in V and U is also an element of V, that means U is also included in this set, that means U dot V is equal to 0 implies U dot U is also equal to 0, right, that is what we are looking at. Then U is the 0 vector. So in any vector space, right, in any vector space you have at least one vector which is orthogonal to all possible vectors in that vector space, and that is the 0 vector. Is this clear? So what we are going to say is the 0 vector is orthogonal to every vector in the vector space, which is basically it says 0 0 all components 0, right, is orthogonal to every vector in V, where V is that vector space that we have already defined. Okay, great. Now what are we going to do? Where are we heading to? So we have proved that okay, there is something called as orthogonality, then we said okay, we have this, we have the what would you call, we said that we brought in the idea of angle here, and then we also said that the 0 vector is orthogonal to every possible vector in the vector space. Now that brings us to a very interesting idea. What is that? We said that if you take a vector space, you look at subspaces of a vector space, right, you look at subspaces of vector space, and how did we define subspaces? Subspace of a vector space is nothing but a subset of the vector space which is by itself a vector space, that is what we said. Now there is there must be a small bulb that should be glowing now. What is that? We said that 0 vector, the set containing only the 0 vector, is also a vector space, it is a subspace of any vector space. We already looked at that, right. We said that if you take the 0 vector alone, it is the trivial subspace that you have, and it is a 0 dimensional subspace that you have. Here is a very interesting clue that we got in the previous case. What was that? We said that you take the entire vector space V here as mentioned here, and what you do, you collect all those vectors which could be orthogonal to every vector in V, right. We already know that V, if it is a vector space, then V is also, you can call it as another trivial subspace of V itself. So, every set is a subset of itself, therefore, a vector space is also a subspace of itself. So, V is a subspace of itself. Now, what we are looking for? We are looking for set of vectors which is orthogonal to every possible vector in V, and we found one element. What was that element that we found? That fellow is basically the 0 vector, and we already know that the set which contains the 0 vector alone is a subspace, right. The set which contains the 0 vector alone is a subspace. Now, we ask this question, can we collect, suppose I have a subspace of, let us say, the vector space V, assume that I have, let us say I have this vector space V, assume that I have a subspace W here. I ask a question, I am going to look at the collection of all possible vectors which are, you know, orthogonal to every vector in W, right. So, I am going to look at this collection, I do not even know what name I want to give here, but I want to look at this collection and then see, look, if I can get some interesting properties of the set of all possible vectors which are orthogonal to every element in W, right. I want to look at that, right. I want to see if something interesting happens, because the existence of 0 vector to be that fellow which is orthogonal to every vector in the vector space has actually given us some kind of courage to ask this question, can that set of vectors which are orthogonal to a subspace be a vector subspace itself. So, we got one vector subspace, the vector space containing the 0 vector alone is orthogonal to every other vector, therefore, the collection of vectors orthogonal to a given subspace, we could ask this question, is that a subspace. So, let us ask this, let W perpendicular be the set of all vectors, orthogonal to every vector in W where W is a subspace of V. W is a subspace of the inner product vector space V. Let us actually say that, okay, I have given this inner product operation also I have defined in V. So, let us say of the inner product vector space V. Because that takes care of my problem. Suppose if I do not define my inner product, then I cannot define orthogonality and stuff. Therefore, I will say that I am going to equip this vector space V with the inner product operation. So, I am going to ask this question, is W or can W be a vector space? Can or is W perpendicular a vector space? We do not yet know, can W perpendicular be a vector space? We really have no clue. So, what we do? Let us see what is there. Let us figure out whether if W perpendicular is actually a vector space or a vector subspace, whatever it is. Let us look at that, right. Okay. Now, how do I mathematically write this W perpendicular? W perpendicular is basically the set of all vectors, let us say U, in let us say this vector space V, right, such that U dot W is equal to 0 for all W in this big W subspace, right. I want to look at this. So, the first question that I ask is W perpendicular non-empty. Because my idea of vector space itself says it is a non-empty collection of elements closed under vector addition and scalar multiplication and the 0 vector being present. So, I ask this question, is W perpendicular non-empty Oh, the answer is an emphatic yes. The answer is yes. Why? Because I at least have the 0 vector, the vector whose components are all 0, which is going to be orthogonal to every fellow in W, because 0 vector is orthogonal to every fellow. The answer is yes, because W perpendicular will at least contain the 0 vector which is orthogonal to every vector so what do you do? Put that 0 vector into this W perpendicular. So let me now give this block a name. I will call this as, let us say, W perpendicular. I am going to call this as W perpendicular. So it at least contains the 0 vector, therefore 0 vector you put it into that basket called W perpendicular, which means the set is non-empty. Now what I am going to do? I am going to take 2 vectors from W perpendicular and then prove that it is closed under addition. We already saw that with inner product, the we saw that u dot v plus w is u dot v plus u dot w. So we are going to make use of all that and I am going to see if there is a closure that happens. Okay. So what I am going to do is I am going to look at this. Let us say let u and v be elements of W perpendicular. Right, I am going to look at u and v to be elements of W perpendicular. Now what do we have? What does that mean? This means I know that u dot W is equal to 0 and v dot W is equal to 0 for this vector W in the W subspace. Is that correct? That is how we have defined our set. So for all W in W I take 2 vectors, therefore u comma v, and then I say that from this W perpendicular I am just going to take u comma v in W perpendicular. So what I am going to say is, look, okay, I am going to say u dot W is 0, v dot W is 0. So what I am going to do? Therefore I am going to say that, look, u dot W is equal to 0, v dot W is equal to 0 for u comma v in W perpendicular and W in W subspace. This implies u plus v dot W is also equal to 0, right. That means if u and v are in W perpendicular, we see that the resultant of u plus v is also in W perpendicular. This implies, right, this implies u plus v is also an element of W perpendicular. Why? Because the dot product with W is 0 for every W in W, right. So therefore we say that W perpendicular is closed under addition, of course with inner product defined, that is always there, inner product is defined in V, right. Okay. Now let us look at this. Let us say take some vector, let us say 3, we are going to say u in W perpendicular. I am going to look at u in W perpendicular and for say some scalar r, for some real scalar r, we know that u dot W is equal to 0 for W in this subspace W, right. Now what am I going to do? I am going to take this scalar multiple, we already know alpha into u dot W. If I do the scalar multiplication, it is going to be alpha into 0, which is 0. Now which I can write it as u dot alpha, I can write this as, sorry, alpha u dot W right. Now what does this mean? This simply means the scalar multiple of u is also an element of W perpendicular. That means if any vector is orthogonal to, let us say, W, a vector in the W subspace, the scalar multiple of that particular vector u, which is alpha u, an element of W perpendicular, where u is an element of W perpendicular, alpha u is also orthogonal to W, meaning that alpha u is contained in W perpendicular, which means W perpendicular is closed under scalar multiplication. Now that is interesting. Here you have, here is a set W perpendicular which contains set of vectors which are orthogonal to a subspace W, and this W perpendicular we see it is closed under vector addition, scalar multiplication, and is non-empty with the existence of the 0 vector. Therefore, we call this W perpendicular as a subspace. Therefore, W perpendicular is a subspace of that vector space V, and we have a name for this, right. We have an interesting name for this. We are going to call this as the orthogonal complement, subspace of W. That is pretty interesting. We are going to call this as the orthogonal complement subspace of W. So, whenever you have a vector space V and you have a subspace of V which is W, you can always find a W perpendicular which is basically containing the set of all vectors orthogonal to the vectors in W. So, this is called the W perpendicular is called the orthogonal complement subspace of W, right. This is the orthogonal complement subspace of W. Now, why did we study this? What is the use of studying this? We want to look at something interesting. Recall that there are 4 fundamental subspaces associated with a matrix A. There are 4 fundamental subspaces associated with a matrix A m by n. We will say the matrix real A is a real matrix, that means it contains a real number entries as this elements, okay, real matrix. Now, what are the 4 fundamental subspaces? We know this, we have, let us say, we have this, this is basically the n dimensional vector space, this is basically the m dimensional vector space. We have A which transforms every n component vector to an m component vector, and we have A transpose which is going to transform every m component vector to n component vector. This is what we have, and the 4 fundamental subspaces that we had were basically null space of A, which we called as the kernel of the linear transformation. So, this also had this name kernel. then we had the null space of A transpose, then we had the column space of A, which is also called as the range of A, then we have the column space of A transpose, which was also called as the row space of A transpose, row space of A, which is also called the range of A transpose, right. We had this. Now, so what? We have these 4 fundamental subspaces. It is interesting to note that with this definition of orthogonal complement subspace for any vector space or vector subspace, it is interesting to note that these two guys are orthogonal complements of each other. What is that? The row space of A and the null space of A are orthogonal to each other. The column space of A and the null space of A transpose are orthogonal to each other. So, we have some amazing result here which says, look, the orientation of the subspaces associated with a matrix, that means a matrix A, the 4 fundamental subspaces associated with the matrix A has 2 subspaces on Rn and then 2 subspaces in Rm. The 2 subspaces associated with A on the Rn side, that means the subspaces of the n dimensional vector space, there are 2 subspaces associated and both those subspaces are orthogonal complements of each other, and the subspace that you have on the right hand side, which is basically the subspaces of Rm, they are orthogonal complements of each other. We will quickly prove this result where we will take this guy and we will take this guy and prove that they are orthogonal complement of each other, and it is easy to prove that these 2 guys are orthogonal complements of each other. So, let us just prove quickly that null space of A and the column space of A transpose or row space of A are orthogonal to each other. So, what do? We are going to do that. Claim null space of A and column space of A transpose, which is essentially the row space of A, are orthogonal complements of each other. Right. So, how are we going to prove this, that these 2 guys are orthogonal complements of each other? We will just take that up quickly and we will prove, and we will also come back to another very interesting what would you call it? Interesting observation, that any vector in Rn can now be decomposed into 2 components, one along the null space of A and the other along the row space of A transpose. So, let us look at this. So, suppose I have this, suppose. So, how did we define null space of A? First of all, let us quickly do that. So, null space of A is nothing but the set of all vectors x in Rn, the n component vectors, such that Ax is equal to 0 m by 1. Then the range of A is nothing but the set of all B vectors which can be expressed as Ax, right. That means it can be expressed as the linear combinations of the columns of A. I can write null space of A transpose is nothing but the set of all y in Rm such that A transpose y is equal to 0, but that is n component 0, and then I am going to say range of A transpose is nothing but the set of all C vectors which can be expressed as A transpose, say some y, for y in Rm, here x in Rm. So, this is how I define all these things. So, now what I want to do is I want to prove that these two guys are actually orthogonal to each other. Let us do that quickly. So, what I am going to do, I am going to take say some x in null space of A, right. What does this mean? X in null space of A implies Ax is equal to the 0 vector, m component 0 vector, right. That means this 0 vector, when I say, what does it mean? It simply means for every x in the null space of A, for x in null space of A, Ax is orthogonal to every vector y in Rm, right. Why? Because whenever x is in null space of A, Ax will be 0 and 0 vector is orthogonal to every vector in Rm. So, this is what we have. So, what do I have? This means Ax is orthogonal to every vector y in Rm whenever x is in null space of A. So, what does that mean? I am going to write this as, let us say, Ax, the dot product of Ax with y is equal to 0 for x in null space of A, right, and of course y should be element of Rm. This is fine, y should be element of Rm, right. Now, what does that mean? I can write this as how is this going to be written? We can write this as, let us say, y transpose. Now, this is also equal to, let us say, y dot Ax, right. So, this is also equal to y dot Ax, which is nothing but, let me take this as y transpose Ax, which is also Ax the whole transpose y. So, when I say Ax the whole transpose y, this simply means this is equal to x transpose A transpose y, right. This is going to be x transpose A transpose y. I can write this implies, I can write this as the dot product with x and A transpose y, which is equal to 0 for every x in null space of A, right. I can write this. This is basically, this will boil down to x dot A transpose y, where x is an element of null space of A. That is interesting. So, I have x comma A transpose y, the dot product is 0, and where does A transpose y go? We have seen this, A transpose y goes to the range of A transpose. Therefore, what we see, so what do we see? Therefore, x is perpendicular to every vector A transpose y for x in null space of A and A transpose y in the range of A transpose. This is what it is, which means x is basically an element of the orthogonal complement of A transpose, right. So, I have this is basically the null space of A, this is the range of A transpose. Now, what it says, x is here and every x that you have here is orthogonal to every fellow there. So, you have this, therefore, null space of A is nothing but the orthogonal complement of range of A transpose. You can actually prove the other way also. Therefore, we say that null space of A is orthogonal complement of row space of A, because row space of A is nothing but the column space of A transpose, right. Okay. Now comes the question, okay, why did we study this? Where are we heading towards when we do all these things? We will see all the whatever that we are studying in terms of, this orthogonality, orthogonal complement and all those things. When we do SVD, we will get to understand what all these things mean. It is actually moving towards SVD, and we will also see that when we want to find the least squared solution, which is very common in machine learning, when we do least squared solution, we actually see that will come out, we will see that there is some kind of orthogonal projections involved, projections onto the column space, projections onto the null space, everything. So, we will look at all that in detail. So, what we do is, in the next class, we will be looking at, okay, we have seen the orientation of these subspaces, it is all fine, but the next class I am going to have a question, I am going to ask a question, look, all this is fine, orthogonality implies, okay, suppose I have a set of orthogonal vectors, what can I do with the set of orthogonal vectors? Is there something that I can do with the orthogonal vectors, right? I have, let us say, the vector x is orthogonal to every fellow in range of A transpose. Now, can I do something with this orthogonal vectors? What is the use of having orthogonal vectors? Suppose I have a vector space, let us say I have a vector space V, and I have the say u1, u2, etc., un linearly independent vectors. We know that these form the basis for V, basis for V, we will say V is n dimensional space, right, n dimensional space. Now, the question that we ask is, will orthogonal vectors, can I find the orthogonal vectors here given that I have linearly independent vectors? Can we find set of orthogonal vectors? Will orthogonal vectors help me doing things in a simpler manner? If yes, there is a point in studying about orthogonal vectors. What is the purpose of orthogonal vectors? What is the purpose of orthogonal transformations? We will look at all that in the next lecture, right. So, the question that we are going to stop with here is, okay, orthogonality shows that there are certain interesting things that happen here. So, I want to look at the idea of orthogonal and orthonormal basis. Orthonormal basis for a vector space. I am going to ask this question, how do I get an orthonormal basis? Now, what is it to say an orthonormal basis? What is the use of having an orthonormal basis? And then what we are going to do is we are going to look at orthogonal transformations. What is so great about orthogonal transformations? And then what we are going to do is we are going to look at the idea of projection. So, that will be the topic for the next class. Thank you.